Okay, good afternoon. Just going to do a short video here where we're thinking about statistics. And one of the main topics towards the end of the semester for intro college stats is hypothesis testing. Really, it's at the heart of a lot of what statistics is about. It really gets towards the tools and process in a very sophisticated and serious way. And I just wanted to talk today for a little bit about a couple of concepts that are loose concepts that we're going to tighten up over time to make sense of hypothesis testing. So a challenge that I like to propose for people who are learning about hypothesis testing is, to think seriously for a second about what it would take for you to doubt something you think is true. Okay. So what would it take for you to doubt something that you think is true? Well, I think we need to address the word doubt. Okay. What does it mean in statistics? What does it mean in general? So I think to come to doubt something involves having a set of expectations, right? So if you think something is true, that means you have a set of expectations that thing will kind of exhibit being true over time. And I think for me, doubt creeps in when things I'm not expecting happen. So I'll give you an example. If I expect, I don't know. I expect that I maintain a healthy blood pressure. Okay, that's my expectation, that I have a healthy blood pressure. And if I were to go into, a local store that has a blood pressure machine and I took my blood pressure and it was not healthy, it was, say, too high, that would cause me a bit of pause, right? It wasn't what I was expecting. I went in thinking, my blood pressure will be fine. I decided to take this and it's high. Okay. Well, what if it's just a little bit high versus a lot high? So what if I'm expecting 120 over 75 and I get 122 over 76? Right. Well, I might take into account that this machine I don't know about its accuracy, so maybe it's, has a plus minus, could be off a little bit. I might know some things about blood pressure fluctuating, as the day goes. Maybe I just had a stressful event. Maybe I was just doing some type of exercise. Who knows? My blood pressure is a little bit high, but I'm not that alarmed. I might start to wonder. I might start to take my blood pressure a little bit more to see if that pattern persists. But if I expect my blood pressure to be 120 over 75 and it comes out 140 over 90, that is startling, right? That would be something that would be more startling, and I would doubt kind of a lot of things, maybe the machine, maybe whatever. But let's take for granted that the machine and everything, how it's being measured, which is a big part of statistics, we'll have to talk a lot about. But if how it's being measured is accurate and unbiased and factual, then the fact that I'm running a blood pressure that much higher than my expectation makes me question my expectation. So if I expect 120 over 75 I get 122 over 76, or I get 140 out of, what did I say, out of 90? Right here, I might, it's a little question, but it's not that much. It's not that much. But here, I'm concerned, right? Now, not everything about statistics is about concern, but this is just to illustrate, what we could be thinking about. Put another way, we'll take it out of the medical situation. Let's say you're driving in a car, okay? So you're driving in a car and you have a car that displays sort of, based on how much gas is in your tank right now, how far the car will go on that. So let's say you have a tank and the reader says, okay, you have 40 miles left on the tank. All right. Now, if you get 38 miles after that, you've driven 38 miles, and the car runs out of gas, you might be like, pretty close, right? So it's pretty close. That 40-mile thing that it said when I turned on my car and I was going to go for this drive, it was pretty close to what I expected. But if you get 20 miles, you might start to wonder what has happened here, right? Is it possible that the reader at 40 miles left was wrong? Maybe it's broken, for example. Or if it says 40 and you drive for 90, you might equally kind of wonder, well, what the heck is wrong with this sensor? Now, it doesn't always play out that way because you watch it and that thing fluctuates in real time. But it's a good thought experiment. Let's say you just looked at it and it was 40 and then the meter itself broke. So you never got to look at it again. So you weren't able to read it. If it said 40 when it was working and then it broke right away, well, you would kind of hope or be expecting that it's going to be 40, right? Now, the further it is from 40 miles, the more kind of skeptical for me, the more doubt creeps in that the meter was correct in the first place. Taking it back to this question about the blood pressure, if I'm getting 140 over 90, the more doubt I have that the initial assumption of 120 over 75 was right in the first place. Much more doubt for this than for this, right? 122 out of 76 doesn't really make me doubt. I mean, similarly, 118 out of 75 wouldn't make me doubt too badly this initial assumption. Now, that is the epitome of what hypothesis testing is going to be using to make conclusions. Ultimately, the true nature of what you're doing with hypothesis testing is not to prove something is true. Okay? What you're setting out to do is to prove that it's not false. Okay? Or at least test that it's not false, right? So at times you may prefer or hope for an assumption to be true or false, based on what they are. Is a medicine going to work? Well, you want the hypothesis that it's not going to work to actually be false. That would be ideal, right? So what we can say is basically that any quantitative assumption that we test in statistics is likely going to be able to be stated as a null hypothesis. Just a fancy way, technical, long history of these terms of stating this is my assumption. This is framing my expectations for what I'm going to see in the world, in the data. So the null hypothesis is tested. Now, what does that mean? It means that you are working from the perspective that the null hypothesis is true. You're not saying it's true, but you're going to work under the assumption that it is. Because by making that assumption, it gives you a frame of reference for how rare what you actually see in the data is. Right? How rare what you actually see in the data is. So let's go back to the 40 miles. Okay, it seems reasonable to me that any sort of measure of how many miles you're going to get back, we know that it has to do somewhat with how fast you're going, how consistently you're braking, how much you need to accelerate. So highway mileage tends to be better, at least in gas-powered cars, than city driving, so on and so forth. And so what we really are thinking about by saying like, okay, our null hypothesis is that, it's 40 miles. What we're really talking about is a null hypothesis that's a distribution around 40. And in this case, I'll say it's a normal distribution, fairly common. So what we're assuming is that, okay, we turn on the car, it says 40 miles, and then we cover it up with tape. How close are we going to get to 40 miles? Well, we're not going to feel that bad about the assessment of the machine that you have 40 miles if you get 39.9 miles or 40.1 miles. You're not even going to feel that bad, in my opinion, if it's like 41 or 39 or even 45 and 35, though I'm starting to stretch it out, as you can tell, right? And the question is like, basically, how far away from 40 miles do you have to get before you actually start to wonder like, well, that wasn't just a rare occurrence. It wasn't just that something interesting happened in the car. It's actually that the reader might be wrong in the first place, and the 40 miles when we turned it on was actually not accurate. So it's maybe not reading how much gas is in the tank correctly. So how far away is that? Well, is it 30 miles? Is it 25 miles? Is it 50 and 55? Is it 60 and 20? How far away, how rare is what you see in data compared to what you expect? Question. Okay. This is at the heart of what's going on here. How rare is what you see in data compared to what you expect? So we'll take a final example to talk about today. Let's go back to last week. We talked about light bulbs. Okay. So say the scenario was basically we're thinking about maybe we have this big building, so take a school or an office building. You have a lot of the same types of lights. You're going to want to buy, the same light bulb for all those lights if they're the same type, because then you can control to some extent, ideally, like how long they last and how frequently you'll have to replace them and the preparation to replace them, because there's some labor and time that goes into changing them. So if you can expect that they're all going to burn out within a few days of each other, that would be awesome, because then you could just, as soon as one burns out, you can make a decision and just say, let's just change all of them. They're all going to burn out in a few days. So you can kind of tell like what the logic of this kind of tight distribution would be. But let's say then, you're looking at different brands or whatever, and you find one that says, guaranteed 100 days, right? Something like that. I mean, you don't have to. This is just an analogous situation to things we encounter all the time of like kind of money back guarantees or like expectations for products, right? So guaranteed to last 100 days. That guarantee is pretty dicey. Let's just say expected to last 100 days, and then you flip it over and in the back it says in small print, plus minus 5 days is the expectation. Now they're setting that based on knowing kind of what the distribution of their light bulb lifespan is. So 95 days to 105 days, the majority, vast majority perhaps, of light bulbs are going to be in there for them, or at least above 95. Okay. Well, without taking for granted that they've done accurate work and that they know what they're doing and that they're not being misleading, if we assume that what they said on the box is true, 95 plus days, what we're expecting, kind of averaging around 100, and we have, ask yourself this question then, how many days do all the light bulbs have to work for you not to question that? For you not to question their claim that it'll run about 100 days or plus? Is it that they all have to make 100? Is it that they all have to make 95 because that's what they said? Is it all that they have to make 94, 90, 85? It is possible, conceivable, that you just get a broken bulb, right? Something is just wrong with a bulb. But what if multiple bulbs stop working at 85 days? When do you cross this threshold of wondering and saying, no, what I'm seeing, so it would be very rare for one of these bulbs to die at 80 if they're saying that 99% of their bulbs last 95 days. It'd be very rare. Not out of the question. But without any extenuating circumstances, it didn't get broken or physically hit. There was no short circuit or, who even knows, a lightning strike, who knows, something that would fry the bulb. Without any extenuating circumstances, if you get 80, you might be like, oh, that's kind of weird. But if a bunch of bulbs are 80, say across a bunch of different places, there's an accumulation of data that starts to push against the initial claim, right? So it's not about necessarily right away establishing what the claim should have been. It's about assessing the initial assumption, the expectation that these bulbs would last a certain amount of time. And if they don't last that long, how short is an issue, right? How short is short enough to make you wonder about the claim in the first place? So there's a lot going on there, and it's a complex idea. This is just going to give you a glimpse today of the logic, the thinking behind what we're doing with hypothesis testing. We are assessing an expectation against data. So we have bought this 1,000 light bulbs for the office building. Our expectation based on the ones we bought is that they should last about 100 days, 95 or above at the very least. If they all start burning out at 80 days, we have very good cause to doubt the claim. If they all start burning out at 90 days, we have maybe decent cause to doubt. If they all start burning out at 94 days, maybe. They all start burning out at 96 days. No, we have no reason to doubt the claim. That is what they claimed in the first place. There will always be a distribution. Even if they say 100 is sort of the number that they're pointing at, they're usually talking then about, and in general, we're talking about means, the mean, the average should be 100 days. But there's a distribution always when it comes to the physical and social worlds. Not everything is clockwork, even clocks aren't in the theoretical sense. So you're looking for plus minus as always and saying there's an acceptable range here of rarity where things are common enough. Yeah, I could see it, that type of thing. Okay, it's a little less or a little more than what I expected, but it's close enough. And that is the epitome of what we're doing. We are assessing when things aren't close enough to the expectation to not question it. So when things are rare enough in the real world, we point then to question. We take that as doubt. It should help us admit some doubt to the initial assumptions that we're making, whether it's the box is accurate on the light bulb, whether it's the reader on the car is accurate, whether it's my expectation for my own blood pressure is accurate, right? So hopefully that's helpful. We'll talk more about this soon.